start with okay, so let's get on to resolution. So before we get on to resolution, let's do some recap. Yeah. So one thing, of course, is easy to show that if you take closed formulae, basically all closed formulae behave like propositions. Right. So in fact, so if you take only closed formulae, then the concept of logical consequence is very much like that of that in propositional logic. Yeah. So essentially, of a closed formula psi is a logical consequence of a set of closed formulae phi, if and only if phi union not psi is unsatisfiable. Yeah. Okay. So some of the things that we have been looking at. So for one thing is, so if you look at all that we have done in essentially in model theory and validity in terms of unsatisfiability, then essentially a non-empty set phi of closed sigma formulae is unsatisfiable if and only if it contains a non-empty finite unsatisfiable subset. And this in fact follows straight from the compactness theorem for closed formulae. So this particular the essentially the contrapositive of this if and only if gives you essentially what I might call a finite unsatisfiability corollary, right. So a set of sigma closed formulae has a model if and only if every finite subset of sigma has a model. So it does not have a model if and only if there is at least one finite subset which does not have a model. Yeah. So unsatisfiability from compactness, actually you get your finite unsatisfiability result for closed formulae. Right. Then a set phi of a closed sigma formulae has a model if and only if it has a Herbrand model. So in fact, this is, so Herbrand's theorem is a very powerful theorem which actually, so these four statements are equivalent to each other, and if you look at these g of phi and then g of phi essentially consists of there are no free variables in g of phi. So valuation is of no effect. There are no quantifiers also in g of phi. So there are no free variables and there are no quantifiers. Then it means that it basically behaves like propositions. I mean, so this is actually the reason why we first learn propositional logic before we come on to predicate logic, because many of the techniques that we want in predicate logic have their direct analogues in propositional logic, and that is also a top down approach, because if you look at predicates as parameterized propositions, then it is a good idea to first get an overview kind of language whose properties we understand thoroughly, and after that reduce everything in a deeper language. It is essentially a deeper language, right. You are looking into the structure of propositions and finding parameters to get parameterized propositions or predicates. Yeah. So and then reduce all that to your language. It's an interesting way of dealing with the problem. And so what are Herbrand models? What Herbrand's theorem essentially says, therefore, is that you take this set of phi of closed sigma formulae. All we need to do is to deal with the ground terms, the ground formulae, and the ground formulae are all quantifier free and variable free, and therefore they are essentially like propositions. Okay. So this has a model if and only if it has a Herbrand model. So which essentially means if the ground formulae of phi have a Herbrand model. Yeah. And the Herbrand's theorem also tells you that we need to deal with only terms in a language. We do not need to go further than that. Yeah. Okay. So any non-empty finite set phi of closed sigma formulae is unsatisfiable if and only if the big AND of this set of closed formulae is unsatisfiable. Yeah? Because they are all closed formulae, they essentially behave like propositions, and from this it is from the first point it is clear that you should just take a big AND. But notice that none of these things might work directly if any of the formulae in phi were open. The moment you have free variables and you have what might be called open formulae, then it becomes important, unless the validity of the formula is established to be independent of those free variables, it matters what interpretations, what models are you looking at, what valuations you are looking at, and that's so this. So for example, the reason the deduction theorem from propositional logic does not directly go into first order logic is precisely because of the presence of open formulae. So there are deep constraints that you have to put on the free variables before you can get an analog of the deduction theorem for predicate logic. Yeah. On the other hand, what all this essentially says is that if you don't have any free variables, and if you then you can treat predicate logic essentially like propositional logic. In the case of closed formulae, there is an added complication that as propositions, a universally closed formula can have an infinite number of ground terms, but that is where the compactness theorem comes to your rescue. Yeah? So, both the compactness theorem of propositional logic and the compactness theorem of first order logic essentially tell you that, okay, for there might be an infinite number of propositions generated by the ground instances, but if I am looking at it not as validity but as unsatisfiability, then I have to look for only a finite subset which is unsatisfiable, which is technically that's a very important result. Yeah. Okay. So then what we did was we showed that we showed the Skolem normal form, right, which essentially says that for any closed formula phi, there is a simple algorithm SCO which generates a formula psi which is not logically equivalent to phi, unlike in the case of propositional logic where we had the conjunctive normal form. Here it is only equisatisfiable. So, they are said to be equisatisfiable. They may not have the same models, but if one has a model, then the other also has a model. And in fact, actually what happens is that intuitively speaking, the process of Skolemization is such that actually every model of the Skolem form would also be a model of the non-Skolemized form, but not necessarily the other way around. I think there is an exercise somewhere where I think we showed that phi Skolemized phi is a logical consequence of phi. Yeah, and that shows that basically what we are saying is that if phi does not have any models, then the Skolemized form of phi also is not going to have any models, right. So, model construction and unsatisfiability therefore go hand in hand. Yeah. So, phi would be unsatisfiable if and only if SCO phi is unsatisfiable. Every model of SCO phi is a model of phi, but not necessarily the other way around. Yeah. Okay. So this is what your Skolem normal forms give you, and so essentially what we are saying therefore is, so what Skolem normal form theorem and the conjunctive normal form for propositions quantifier free formulae says essentially is that I can therefore up to satisfiability every closed sigma formula may be transformed into a Skolem conjunctive normal form. So, that essentially means it is a universally closed form in a pre-next normal form with a sequence of universal quantifiers followed essentially by a body consisting of only propositional connectives, yeah, and predicates. Okay, so so this is what this Skolem normal form tells us. Okay, so any universally closed sigma formula psi in Skolem normal form, now I am not necessarily talking about the conjunctive normal form, in Skolem normal form has a model if and only if the ground instances of sigma psi have a model. Yeah. So, this is what happens when you take your Skolem normal forms and apply Herbrand's theorem again on them. That's so, after all, your Skolem normal forms are also a subset of your closed formulae. Yeah. So, Herbrand's theorem applies immediately there. So, which means your quest for models and unsatisfiability is essentially restricted to ground formulae. And when you take the ground instances of psi, what are you doing? Essentially, you are throwing out the quantifiers, and you are replacing all free variables in the body by terms, purely syntactic terms, right? And you are essentially looking for and variable free syntactic terms. So, your quest for models, or equivalently the quest for unsatisfiability, comes down to a quest for essentially ground models or ground unsatisfiability, right, which is important because of the fact that when our original thing, if you want to prove your arguments to be valid, then you need to prove that the premises union the negation of the conclusion is somehow unsatisfiable. So, the quest for models comes from there, and the quest for unsatisfiability comes from there. And so, logical validity is also somehow related to unsatisfiability in the same way, and that is what we will use, right. So, this is this is a recap. So, now let us look at it this way. So, a closed sigma formula psi and the universally closed sigma formula scope psi are equi-unsatisfiable. If they are equi-satisfiable, then they are also equi-unsatisfiable. And universally closed sigma formula psi in SNF is unsatisfiable if and only if the ground instances of psi, that means you throw away the universal quantifier by essentially taking all possible substitutions, ground substitutions of the free variables in the body of psi, look at all those as essentially as propositions. If that set is unsatisfiable, then your original formula psi is unsatisfiable, right. So, since g of psi consists of only closed formulae, g of psi is unsatisfiable if and only if there is a finite subset of g of psi which is unsatisfiable. So, everything falls in place. We are interested in proving valid arguments, which means there is a logical conclusion to a set of premises or to a set of axioms, and that for closed formulae in general we are interested in first order theories. So, which means your original set phi will actually be a collection of closed formulae. If they are not closed formulae, and if you are really looking at theories, and if they are open, then they have to be valid for all those models that you are interested in, which means you can also universally close them. So, they should be true for all ground instances, and essentially we are going to try to prove unsatisfiability. So, our current goal now is to just go into unsatisfiability. There is in order to actually show logical validity or logical consequence of some statement from some other statement. Okay. So, let us look at Skolem conjunctive normal forms. Yeah.
You just argued that we can, if the formulae are open, we can universally close.
Actually, what I meant was you most of your first order theories, the axioms are expressed as open formulae under the assumption that they are valid for all the models that you are interested in. Okay. If they are valid for all the models you are interested in, and they are therefore valid for all possible valuations of the variables in the formulae, then they are actually, their universal closure is also valid in those models. That's all. That's really the implication. Yeah. Okay. So let's look at look at a Skolem conjunctive normal form. So these are essentially what are known as a set of clauses, Ci. So there might be for any formula there will be a finite set of clauses, Ci, such that the original Skolem conjunctive normal form should be regarded as being syntactically the same as a universal closure of the conjunction of these clauses. Okay. Where of course each clause consists of a set of literals basically, where the set of literals is to be regarded as, so each clause is to be regarded essentially as a disjunction of a collection of literals lambda j. Yeah. So essentially what we are saying is your Skolem conjunctive normal forms are, as we did in the case of propositional logic, they are just going to be represented as sets of literals. Yeah, that's and essentially there is an essentially there is a disjunction deep inside, and then there is a conjunction at the outer. Yeah. Okay, so that's what. So we will all. So now from now on, what we will do is we will just look at a collection of clauses. They are all finite sets. So these are all finite sets of clauses. So we will just look at a set of clauses where each clause is a set of literals. Yeah. Of course, now what happens is, since we have, so we will actually talk about there being free variables in the clauses. Yeah, because we are actually physically omitting the universal closure. So we are actually looking at clauses with free variables. Yeah. But they are not to be regarded as open terms, because they are supposed to be regarded as implicitly universally closed. Yeah. Okay. So, but however we will talk about their free variables, because what we are going to do is we are going to deal with substitutions of those free variables. Okay. So, a clause is a finite set of literals, the empty clause is the empty set of literals. So, the empty clause essentially represents false, right. Okay. A ground clause is a clause with no occurrences of variables. So, you can take any substitution theta and a clause C. Each literal might have free variables, each literal in the clause might have free variables, and you can actually apply the substitution theta to the free variables. Okay. In particular, so theta C is just theta applied to all the literals in the clause, and in particular if theta is a ground substitution, which means all the variables are replaced by ground terms, then this what you get is a ground clause, a collection of ground literals basically. Yeah. Okay, so for each substitution that is what you get, right. So, if I take a clause C, and remember that it is essentially to be regarded as being universally closed, right. So, for all possible values of the variables in the clauses, you are essentially saying that corresponding ground predicate is true. Okay. So, you can take the set of all ground instances of a clause, and that is essentially take all possible ground substitutions for the free variables of the clause and just take this huge, we are going to essentially take this huge union, but at the moment I am regarding it as creating for each clause a collection of ground clauses. So, for each ground substitution theta, there is a new clause theta c which is completely variable free and which is a ground clause. Yeah. If I have a set of clauses, a finite set of clauses, then the set of ground instances of S is essentially a big union of the sets of ground clauses. Yeah. So, notice that all this is consistent with our interpretation that this set S is implicitly universally quantified over all the variables, right. The only problem sometimes is that okay, so I have some clause. Okay, let me start with a formula. Let's say some particular relation is transitive. Yeah. So then what we are saying is for all x, for all y, for all z. Let's say this is some atomic predicate, binary predicate p, p of x y and p of y z arrow p of x z. Yeah. Okay. So, this is transitivity. And let us say you have symmetry. Yeah. So, symmetry would also be written as for all x, for all y, p of x y, arrow p of y x. Yeah. Okay. Now, if I were to convert these, so I can convert them into Skolem conjunctive normal form. So, this one gives me, okay, or let us just worry about this body. Yeah. So, this body essentially is not of this. So, not p x y comma not p y z comma p x z. Yeah. So, essentially as a clause this is what it is. Yeah. And if I were to take this, then this is just not p x y p y x. Okay. So, as a clause throwing out the universal quantifiers, I get essentially these two clauses. Right? However, since we are talking about these being implicitly universally quantified, it means that this x here and this x here are different x's. Okay. Right. So, that's so actually what we need to do therefore is we need to do an alpha renaming, so that different clauses, since we are throwing out the quantifiers, there is a possibility of confusion. So, you need to do an implicit alpha renaming. If you are going to use implicit universal quantifiers, you should do an implicit alpha renaming. So, if you do an implicit alpha renaming, essentially what we are saying is this we will choose some two new variables which do not occur anywhere else. So, I get essentially not of p, let us say u v and p v u. Yeah. And this process, so if my original set S contained these two clauses, yeah, then this process of separating out the variables is called standardizing apart. Yeah. So, because of the fact that your universal quantifiers are implicit and they have a scope restricted to the clause, you need to do an alpha renaming if you are going to throw out the universal quantifier. Remember one thing, that therefore, essentially what we are saying is that this is if you are looking at the logical consequences of this set S, then you are essentially looking at a conjunction of these two formulae. So there is a logical consequence. So here is a logical consequence, and one logical consequence is for all x for all y do I need a third variable? Probably do. For all z okay, it's transitive, right? Oh, it's also symmetric. Okay. Would this be true? Yeah. So this so if P is a transitive and symmetric relation, then essentially this statement should be right. Okay. So what are we saying now? We are saying that S so this statement is a logical consequence of this statement, of these two statements. So which means that I am saying that I can take the AND of these two statements, and this would be a logical this would be a logical consequence of the conjunction of these two statements. Yeah. Of course, what I said was that we are going to standardize apart, which means you are going to rename the variables, right. What does happen now is, so let us keep this away for the moment. When you standardize apart, you no longer have it in Skolem conjunctive normal form. Okay, when you do the when you include this AND, then you no longer have a Skolem conjunctive normal form. But then what you have is that this AND is, I am going to do some origami here. Okay. So this AND, after having done a standardization apart, which means I replace this by u and this by v, yeah, this is logically equivalent to actually having for all x, for all y, for all z, for all u, for all v, and having a conjunction of the bodies. This is something we I think is there in an exercise for moving quantifiers, right. That's So when we move quantifiers, so essentially then what it means is that I just deal with this essentially this entire body. Yeah. So when I take a set of closed, so it's clear that these kinds of manipulations cannot be done if there are open formulae. They have to be done with only with closed formulae, right? Okay. So anyway, so now let's look at. So essentially, we are going to look at this. Okay. So we have these clauses and their ground instances, and let's look at some other clauses. So one of the things that we are going to do, and in fact, which, for example, all resolution theorem provers do and all prologue systems do, is that regardless of what the user has given, they generate internal temporary variables to do a standardization apart. Okay? And everything within the prologue system actually works only with its internal variables. It's only, but they do maintain a table somewhere during the scanning process which gives the correspondence between the user defined variable names and the internally generated variables, so that when they have to give error messages, they can use the user defined variable names. Otherwise, all prologue systems actually do this generation of temporary variables regardless of what the user has specified. Yeah? So, they do a standardization apart in that form, but the reason for doing that is absolutely essential. Yeah? But we will not let's look at some more properties of clauses. So the first thing is that I take what this has shown me here from here is that I can blindly take universal closures, whether there are free variables or not. So you take a collection of clauses, Ci and Cj will, having been standardized apart, will have different different sets of variables. I take the conjunction and the universal closure, and that's logically equivalent to taking the clauses apart and taking their universal closure. And this is because your universal quantifier is essentially a generalization, an infinitary generalization of your AND. Okay, so it can be moved around, but this universal closure therefore leaves unspecified what variables actually are free in Ci. So if you take these two clauses, for example, this universal closure on the left side corresponds to this corresponds to this, the closure of 5 variables, right? Whereas on the right side it corresponds to one clause with 3 variables universally closed and the other clause with 2 variables universally closed. Yeah. Okay. So here is the reference. So this quantifier movement essentially tells us that we can do all these kinds of manipulations. Yeah. Okay. So that's what our universal closure gives us. So this is one fact. The second is let's look at models of clauses. So we just so a structure A is a model of a clause C, and we will denote it this if and only if the universal closure of the disjunction of literals in the clause is a model, A is a model of that, right. Notice that a clause is a set of literals and we implicitly regard it as a disjunction, as an OR of all the literals. Yeah. Okay. A set of clauses has a model A if A is a model of every clause in S, because a set of clauses is actually a conjunction of clauses, right, implicitly. And a clause C is a logical consequence of a set of clauses S if and only if every model of S is also a model of C. Yeah. Okay. An empty clause has no models, because an empty clause typically refers to the constant false, if you like. Yeah. Okay. So now in the Herbrand's theorem brought down to the level of clauses essentially says that a set of clauses possesses a model if and only if every finite subset possesses a model. And essentially this is more important, a set S of clauses is unsatisfiable if and only if there is a finite subset S prime which is unsatisfiable, with if and only if this G, the ground instances of S prime is not a model, and actually we can go further. There is a finite subset of ground instances which do not possess a model, right. That is what Herbrand's theorem gives you, right. But otherwise, okay. So, now which actually brings us to the resolution method. So, for uniformity, think so let us look at it even from your operational semantics and programming languages. You would have realized that many of the structural rules there had side conditions, right. Evaluation of if then else, I mean, would have two rules where in one rule the then clause is executed and the side condition is that the boolean is true. In another rule the else clause is executed and the side condition has a boolean false, right. Okay. Think of all this as a side condition for this rule, basically. Just think of all this whole thing as a side condition. Okay. So, here what are we doing now? We have a set of clauses S and we choose two clauses Ci and Cj. The way you choose two clauses Ci and Cj is such that they have some common atomic predicate P occurring in them, such that in one of them P occurs in positive form over some terms. By the way, this Si prime arrow is meant to signify the vector, the tuple of ground terms, right, the tuple of terms. So, if P is an n-ary atomic predicate, then you assume that this vector has a length n, yeah, there are n terms there. Okay. So, basically it has some set of terms of P and the other one has some negations of terms of P. But of course, there is no reason to believe that this Si prime in any case is related to this Tj prime. Firstly, there are two different clauses. So, one of the first things that would happen is that you would standardize them apart. So, anyway the variables are going to be different, right. Okay. But that apart, so what you do is, supposing you have this, and what you can do is you take these two. So, Ci is Ci prime union some, you can have more than one occurrence of the same atom with different parameters, right, terms within the same clause. So, that is why I have taken this to be a set. Assume there are mi clauses in Ci which basically have the atom P occurring with various kinds of n tuples of terms, and similarly in Cj maybe there are mj different occurrences of the negation of P with various kinds of n tuples of terms. Yeah, I take the union of these two sets, okay, except that I am sorry, this negation should not be there. Huh? This assume it. Okay, I take this union, remove this negation, and I see whether this is unifiable. Okay. So, one of the things we did initially was we standardized them apart. Then now what we are saying is, can they be all made to look alike? Okay. If they can all be made to look alike, then my unification algorithm gives me some most general unifier mu. Notice that these Si primes and Tj primes, they do have variables in them. So, at this stage we are not talking of a unifier which will be ground. It will still have variables in it. Okay? It will have variables in it, it is not ground. So, we are not actually using that last part of Herbrandt's theorem, but what we are saying now is in S I can remove these two Ci and Cj and take the unified version of Ci prime union Cj prime, and essentially what I am saying is that this so this is a clause, right, the unified version of Ci prime union Cj prime. It can have free variables. Your most general unifier does not necessarily make things ground. So, it leaves some, it keeps lots of free variables, which means that as a clause it is implicitly universally quantified on all those free variables, right. And so, essentially so this is the resolution rule, which just says that I start with this S and I take, and then I essentially replace this Ci and Cj in S by this unified Ci prime union Cj prime. Unlike the case of propositional resolution, there are various differences here. One is that in propositional resolution, we had only one atom and its negation, right. Here we are saying that it is possible to take a set. So, I mean this is not just a cleanup problem. I mean this is I mean in the case of propositional resolution, I said that you have to clean it up so that you didn't have multiple duplicate copies of atoms lying around, yeah, because then that will destroy your empty clause. To make your empty clause a non-empty clause, and that. But here it is not. Here it is deliberate. It is not even that you choose. It is not even that you choose all possible terms with p in it here and all possible terms with not p in it here. No. It is not even that you choose a maximal subset which is unifiable. No, not even that. You choose some unifiable subset. That is it. Yeah. So which means that in Ci prime there could be various occurrences of p hanging around still there. There could be occurrences of not p also hanging around there. And similarly in Cj prime there could be occurrences of p with various other terms and various occurrences of not p also with various terms. It does not matter. All we are saying is you take, we are not even saying you should take only one, you take some subset which is unifiable. And the result of this application is essentially that the universal closure of mu Ci prime union Cj prime is a logical consequence of Ci and Cj. Right?
So, what happens when we are not able to find such a unifier?
Then it is not unifiable.
And then the clause is not satisfiable. The set of clauses is not satisfiable. Is it an implication?
Okay. So there are two aspects to resolution. Okay. When you look at resolution theorem proving, you are looking at logical consequence. Okay. When you look at resolution refutation, you are looking at unsatisfiability. Okay. So, all your prologue systems work on a form of refutation, resolution refutation, but I will come to that later, which basic resolution refutation essentially means that I should be eventually able to, by applying this resolution rule several times, I should eventually be able to derive the empty clause as one of the members of the set. And if the empty clause occurs in the set, so take this denominator to be the set S prime. Yeah. If the empty clause is a member of this set, then what you are saying is that you have refuted the argument. Yeah. So for that, what you are going to take is so So, you can either try to prove for a given set phi for a given set of formulae phi, you can either prove psi is a logical consequence of phi, or you can include not psi there and prove a refutation. So, both of them are possible. In the second case, what you have to do is you have to explicitly derive an empty clause. In the first case, if you can actually derive psi from S, well, that is just as good. In fact, that is what we are going to do now. Yeah. So, let us take this example. So, the interesting things about resolution is that this is like a new single proof rule, and you do not need any other axioms or proof rules. So, what I am saying is you throw out the whole of Hilbert style and Gensen style proof systems, throw them out completely. Take predicate logic and have just this one rule with this complicated side conditions. And what we will be able to show later is that this one rule is sound and complete for predicate logic. Yeah. So, resolution, so the entire you can have, so this is called the resolution calculus. The resolution calculus just defines the language and has this one rule, finished, that is it. And with this rule, hopefully you can, you do not require any other axioms, nothing, you just have to apply this rule repeatedly. It might require some intelligence to apply this rule in order to get logical consequences. So, getting logical consequences by just this rule is not deterministic, it will require some thought, but your refutation procedure can be deterministic. So, if you compute logical if you want to calculate logical consequences by taking the negation of the conclusion and then deriving a refutation, that can be done deterministically. And the determinism actually stems from the MGU. What does the MGU give you? It says that I only do as much, I do not rush into doing a ground substitution. I make them look alike with the minimum number of substitution changes which will make them look alike, and I still retain the variables, because what I am going to do essentially is, after this when I have got S prime, I am going to look for another resolution mechanism, another application of resolution. That application of resolution might again involve only the same atomic predicate P, but and each time, so that I am basically composing my substitutions gradually without making too many commitments and doing it sort of opportunistically. I am waiting till the right moment in order to do a certain minimal substitution to make things look alike, derive a new clause and then apply again, and so on and so forth till I get maybe an empty clause from the form itself. So, I may not get you an empty clause directly from ground instances. Okay, so there was that theorem we proved, right, before Herbrand's theorem, that if I had a set of ground instances in the form of a clause, where is that? Okay, we do have time to hunt that out. Wait, ground instances, Herbrand's theorem. There are the sets of ground formulae, right? So, take a look at this lemma. This is a set of ground quantifier free formulae, but the difference is that by taking MGUs, we are not rushing into ground formulae, because what this allows us to do, for example, is where was that thing with all those big wedges and so on. Oh, we reached the low now. Hey, I had one lemma somewhere. Maybe it is. Here it is. Okay. This ground quantifier free formula, we had this theorem, right, which showed us that you can just do pattern matching. So this OR of lambda I is like a clause, right? Okay, and this checking complementary pairs is just a pattern matching, looking for identical trees with a negation, right, on one side. So instead of going right down to ground formulae, by using MGUs, we are staying within the level of clauses with free variables in them, but if the patterns still look like complementary pairs, then anyway it is not necessary to go down to the ground. So what I mean is, even if I have variables and after unification I get one clause which has, let us say, p of x and another clause which has not p of x, not p of of course after if okay, I can actually decide to resolve between them, do a common substitution of a variable minimum, right, absolutely minimum. So maybe I decide to replace y by x, then I get a complementary pair, but this complementary pair is not ground. At the level of all I am saying is that it does not matter this this is always a complementary pair, whatever substitutions you make for it, right. So our MGU allows us to postpone that decision till an appropriate moment, right. So we are not using that. So we are just using MGUs because of, yeah, okay, we are just using MGUs so that we look for an appropriate place when we can decide that something is a complementary pair, but it is a complementary pair not necessarily of ground instances. If it is not of ground instances, then they are not propositions. If they are ground instances, they are essentially propositions, but these are like propositional forms with variables. So this is like a typical contradiction in propositional logic, but with variables, right, and this is always going to be a contradiction, right. So let's just look at this. So what we do, so we can actually prove, okay, so having standardized apart, what you can actually do is, I want to prove this xy and xz pyz, right. And actually I have to choose an appropriate so this one, by the way, what is the form of this? This one would work out to not p xy or not p xz, p yz, right. Okay, so what I am going to try to do is, so these are my clauses Ci and Cj. I have to choose some subset here and some subset here which are complementary, unify them, find the appropriate substitution, do that substitution throughout, and essentially derive this. Okay. So, so one thing is clear. So, there are two negations here, one positive occurrence, here is one negation, one positive occurrence. So, so I have to take either this positive occurrence and this negation, so that I get these two negations and this positive. So, you have to find one substitution, and there is a substitution which at the moment I am not able to clearly see, but I think what you can do is yeah, either way, actually either way, supposing we take this, supposing we take this and we take this, okay, and we unify, okay, then I get this not p x y which I want. I get this, I get not p u v, but then if I am going to unify it with this, then this u v will get substituted by x z, okay, such that let's put it this way. I find a substitution theta so that this thing becomes not p x z, yeah. So, which means I am going to replace u by x and v by z, probably. This might work, is it? No, that may not work. It may not work with this. So, okay. Y z. So, okay. There is one particular substitution you can find, which at the moment I am not able to see, but I'll do that and show it. But basically, what you can do is you can find a substitution, apply it, and then you will get this clause, and then that's like a logical consequence. Yeah. Okay, let's stop here at this point.